astronomers, without using like machinery or equipment, can judge the brightness of the star down to a decimal point and record accurately the brightness of the stars. Now the people doing the really careful work have, you know, some gizmo that does that, right? So anyway, there it is, right? So minus 27 is, you know, don't look at it too much, right? 1 is a normal bright star. 6 is barely visible to a naked or unclothed eye, but of course you can't see anything if you clothe your eyes, right? And then this whole thing here is that basically, if you remember with logarithms, if you go down by 5, the way this thing works out is it's a factor of 100, but we're not going to get into that. Okay? And then the final thing is that there's something called absolute magnitude, right? So apparent magnitude, the little m, is a factor of all of these things. Let me draw a little diagram here. Okay? The apparent magnitude is a factor of all of those things, okay? But absolute magnitude is an intrinsic property of the star. It's related to this, okay? So the big M is related to that, little m is related to this. This one is our apparent magnitude, how bright it appears. So with apparent magnitude, you don't know whether it's a bright star far away or a dim star that's close to us, right? They could both have the same apparent magnitude, but absolute magnitude, when they talk about absolute magnitude, that's how bright the star really is. It's intrinsic brightness. That's why it's called absolute, yeah? So if you ever are like texting somebody from another, you know, solar system, right? You know, and they start bragging about how bright their star is, ask them how far away they are from their star. They might be like really close, and their star might not be so bright after all, right? You know, so don't let them get away with that. You know, right? So for temperature, hot is bright, size big is bright, distance far is dim, not bright, right? Okay. And apparent magnitude is a combination of all of them. Absolute magnitude is, and the definition, by the way, is it's the apparent magnitude at a distance of 10 parsecs, right? If you were 10 parsecs from that star, that would be its absolute magnitude. It's, right? That's not so important, but this is. Okay? So this is somebody, these guys, and if you are naming your child, okay, if you've got a child to name, don't discount the name Enyar, right? That's a fine name, right? Enyar Hertzsprung and Henry Norris Russell of the HR diagram. What they did was they made a very bad graph. Let's look at this graph. Okay? This is pretty good. This axis here is the brightness of the star. Okay? This axis here is the temperature of the star. Right? So let's draw a little picture of that. Okay? On an HR diagram, this is brightness. And on that diagram at the bottom of your page, don't you have a diagram there? Yeah. Right? Label the top bright, dim. Now, that axis looks messed up. But it's not messed up, it's right. But the negative numbers are at the top, right? But remember, negative numbers are really bright stars, yes? Now, with this negative number here, this is not apparent magnitude, this is absolute magnitude, yes? Yes, so this is good. A -2 here, okay, means that that's a pretty darn bright star, right? And then a 12 is like, we couldn't even see it if we were 10 parsecs from it, right? Okay? And then this thing here is screwed up. The temperature on the bottom is screwed up. Why did they do it this way? I don't know why. Okay? But they've done it, and it's too late to change it. Everything's all, messed up, right? But this, on this side, okay, is hot, and this is cold, right? Shouldn't it go like cold to hot, temperature-wise? Yeah, I don't know why. Well, the original thing, by the way, the original axis is spectral type. They actually had all these little spectral types that they went in there. But if you make this graph like this, the graph makes a kind of a whoa, kind of a thing like that. This thing is called the main sequence. Most stars that are undergoing hydrogen fusion, they are turning hydrogen into helium. They are fusing atoms together, which releases a tremendous amount of energy. This is a hydrogen bomb, uses the same basic reaction, right? stars that are undergoing hydrogen fusion will fall on the main sequence somewhere. Yeah? These stars on this end are supergiant, super hot stars. These are giant hot stars. Okay? And these stars on this end, label that on your little thing. Okay? These stars on this end are small, cool stars. Notice that I labeled them in red and blue, and that's because these guys are blue and these guys are red. That's their temperature. Temperature is related to their color. The hotter they are, the bluer they are, the cooler they are, the redder they are. Okay? Now we've got some mysteries. We've got some mysteries. Let's take a look at these guys here. These guys are cool, but very bright. Shouldn't a cool star not be so bright? Yeah, so how is it that those guys could radiate so much energy? They're big, yeah. So label the red giants, these guys out here, okay? These guys are the red giants. And the reason why they're so bright is their size, right? These guys are big. They're not on the main sequence, by the way. They have actually left the main sequence and they're about to go on to more exciting things like helium fusion and stuff like that. They've left the main sequence, right? Here's some other mysterious stars, right? These guys are very hot, but not very bright. Yeah? I was going to make a joke about a celebrity, but I'm not going to say that. Like Charlie Sheen. But anyway, whoops, that wasn't out loud. Okay, anyway. Very hot, but not very bright. Why are they not so bright? Because, well, the other variable that you can infer from this is size, can't you? So from this graph, you can actually read the temperature and you can read the brightness off the graph, right? Can't you? Temperature and brightness, can't you infer the size? Yeah. So we're gonna do a few of these things, right? So the dwarfs, the white dwarfs, and if you're inclined to call them white dwarves, okay, you've read too much Tolkien. Dwarves is not actually a word with a V. I used to think it was until I think 3 years ago. Okay, but it's actually dwarfs, white dwarfs. But in Tolkien there are dwarves, aren't there? Yes? Yeah, there are dwarves. Anyway, these guys, label these guys small. Right? Okay, now let's take a star here. Let's pick a different color. I have a different color. Okay, let's pick a different color. Let's suppose I have a star and it goes from here and it goes like this. What happened to that star? What happened to its temperature? What happened to its brightness? What happened to its size? Anybody tell me any one of those. What happens to its temperature? What happens to its brightness? What happens to its size? Now temperature you can just read off the graph. Okay, so yeah, so the ones we can read off the graph are that it moved this way, didn't it? So didn't it get colder? Like the ACT test, right? And didn't it go that way? So didn't it get... It got brighter. How do you get colder and brighter at the same time? You had to get bigger. This guy had to get bigger. The size had to get bigger because normally when you get colder, what happens to you? You get dimmer, don't you? So this thing had to get bigger, right? Don't put your stuff away, please. Okay. What if a star does this? What if a star does this? Staying the same brightness, but it's getting colder. Well, if you get colder, you should get dimmer, right? Yeah, so how is this star getting colder but not getting dimmer? It's getting bigger too. There we go. That's good. We're inferring stuff here, aren't we? Yeah, this star has to get bigger to do that, right? It has to compensate for its lack of temperature by getting bigger. Pretty much anything on this side is going to get bigger. And let's try another one. What if I do this? What if I have a star that goes like that? What's happening to it? What's happening? Is it getting any brighter? No, it's not getting brighter, but it's getting hotter, right? So this guy's getting smaller, right? So these guys are bigger. What if it does this? What if it goes straight down? It's getting dimmer, but is its temperature changing? No, so it's got to be getting smaller.